Let's talk about Galileo Galilei, a true giant in the history of science. He was the scientist who fundamentally changed how we understand the motion of falling objects, challenging long-held beliefs and paving the way for modern physics. The most famous story, though perhaps more legend than documented fact, says he conducted an experiment at the Leaning Tower of Pisa. He supposedly dropped 2 balls of different weights from the tower, all to demonstrate a key principle: to see which would land first. Back then, nearly everyone, even learned scholars, believed Aristotle, that heavier things fall faster than lighter ones. It seemed intuitive, a common-sense observation. But Galileo, with his inquisitive mind, questioned that fundamental assumption. Through careful reasoning and experimentation, he discovered that, without the influence of air resistance, everything falls at the same rate. Whether it's a heavy bowling ball or a light tennis ball under ideal conditions, both would hit the ground at virtually the same time. But Galileo wasn't satisfied with just disproving Aristotle. He wanted to know more. He wanted to understand the of falling motion, not just objects fall together. He sought a deeper understanding of the underlying principles. To study this, he ingeniously used ramps to slow down the motion of falling, carefully rolling balls down these inclined planes and meticulously timing their descent with water clocks, which were the most accurate timekeeping devices of the era. Through countless trials, he began to notice a consistent pattern emerge. He observed a clear relationship in the distances the balls traveled over equal successive time intervals. The measured distances weren't just random numbers, they exhibited a predictable order. They followed a precise mathematical rule, a hidden harmony in the seemingly chaotic world of motion. This discovery became known as Galileo's law of odd numbers, a seemingly simple observation born from careful experimentation that ultimately led to a major breakthrough in our understanding of physics and motion. It's a powerful demonstration of how meticulous experiments and careful observation can unlock the hidden rules and fundamental laws of nature. So, what exactly is Galileo's law of odd numbers? It sounds a bit mysterious, doesn't it? But it's actually a fundamental principle that helps us understand how objects fall under the influence of gravity. At its core, it states that in equal time intervals, meaning if we break down the fall into consistent chunks of time, a falling object covers distances in the ratio of odd numbers. This is a key observation about the nature of acceleration: 1, 3, 5, 7, and so on. This sequence continues infinitely, always following the pattern of odd numbers. Why does this happen? Because falling objects accelerate. Their speed isn't constant. They go faster and faster each second as gravity exerts its force. In the first second of its fall, it covers a certain distance, let's call it d. This is our baseline. In the next second, because it's accelerating, it covers 3 times that initial distance, or 3 days. And in the third second, it covers 5 times the original distance, or 5 days. The pattern is always odd numbers for each interval, showing the increasing distance covered due to constant acceleration. It's important to remember that this refers to the distance covered each time interval, not the total cumulative distance. It's like tracking how much farther you go each hour on a road trip, not how far you've traveled in total since you started, as you speed up and cover more ground in each subsequent hour. This law reveals a hidden rhythm and order in what might seem like a chaotic process of how things fall, one you can actually measure and verify through experimentation. It's a simple yet beautiful and elegant code that underlies the math of motion, revealing the predictable nature of gravity's influence. Let's break down the pattern. 1, 3, 5, 7. When an object falls, gravity accelerates it at a constant rate, about 9.8 meters per second squared. In the first second, it covers a base distance, call it 1 unit. In the second second, it covers 3 times that. In the third, 5 times, and so on. Add up these distances. After 1 second, it's 1. After 2, 1 plus 3 equals 4. After 3, 1 plus 3 plus 5 equals sign 9. After 4, 1 plus 3 plus 5 plus 7 equals sign 16. Notice the totals? 1, 4, 9, 16. Those are perfect squares. So, the total distance fallen is proportional to the square of the time. Galileo's law not only explains the pattern in each interval, but also why the total distance matches t2. This was a huge leap in understanding motion. Simple numbers, big discovery. Let's see Galileo's law in action. Imagine dropping a ball in a vacuum, timing each second. In the first second, it falls 4.9 meters, our base unit, d. In the second second, it falls 3 days, 14.7 meters. In the third second, it falls 5 days, 24.5 meters. Divide each by 4.9 comma, and you get 1, 3, 5, the odd number pattern. The data matches the law perfectly. Galileo's odd numbers aren't just theory. They show up in real measurements. This fundamental law connects directly to the equations you learn in physics class. It's not just an abstract concept, it's woven into the very fabric of how we understand motion and gravity. Understanding this connection can make those equations feel less like arbitrary symbols and more like a description of the world around you. Take, for example, the formula S equals sine 1 half t2. This elegant equation gives us the total distance, represented by S, that an object falls after a certain time t has elapsed. It's a simplified version of a more general equation, but it perfectly captures the essence of free fall from rest. Let's put some numbers to it. If we use the standard value for the acceleration due to gravity, g equals sine 9.8 meters per second squared, then after 1 second, the distance fallen s is equal to 4.9 meters. This is a direct application of the formula, showing how quickly an object accelerates downwards. Now let's double the time. After 2 seconds, the total distance fallen is 19.6 meters. Notice how the distance doesn't simply double when the time doubles. It increases much more rapidly due to the squared term in the equation. And after 3 seconds, the object has fallen a total of 44.1 meters. The increasing distances highlight the accelerating nature of gravity. But what about the distance covered each second? To find that, we subtract the distance fallen at the end of the previous second. So the distance covered in the second is 19.6 meters minus 4.9 meters, which equals 14.7 meters. Similarly, the distance covered in the third second is 44.1 meters minus 19.6 meters, which equals 24.5 meters. Now, let's compare these distances: 4.9 meters, 14.7 meters, and 24.5 meters. Do you notice a pattern emerging? If we divide each of these distances by 4.9 comma, we get a sequence of numbers 1, 3, and 5. This simple math elegantly proves Galileo's law of odd numbers, which states that the distances traversed during each successive second by a falling object are proportional to successive odd numbers. It's not just a historical anecdote or a quirky observation, it's a principle deeply built into the physics you use every day to understand motion. Understanding this law helps you see the real-world meaning and implications behind the seemingly abstract formulas you encounter in physics. It serves as a crucial bridge, connecting the theoretical world of equations with the tangible reality of experiment and observation. Galileo's profound insight, revealed centuries ago, is still very much at the heart of what you learn in physics class today, providing a foundation for understanding the universe around us. Why does Galileo's law matter today? It was a turning point, showing that nature follows mathematical rules we can discover. It laid the foundation for Newton and modern science. For students, it makes acceleration real and visual, not just a formula. The law helps you connect math to the world. Every time you drop something, you see it in action. It's used in engineering, sports, even space travel. Galileo's curiosity reminds us, simple questions can reveal deep truths. The next time you see something fall, remember, you're watching 4 centuries of science in motion.